here. And so the idea is very simple. If these WIMPs fill the halo of this galaxy, although rarely from time to time they care to scatter off a nucleus of an atom, and we can calculate the energy which is imparted to the nucleus. It's an elastic collision, and that energy is the first challenge that we face as an experimentalist, to try to see this dark matter particle through this process, because the energy can be calculated to be very tiny, a few tenths of electron volt or less depending on the target. So the observable is this kinetic energy which is imparted to the nucleus. And before I move on, for now, for a long time we've been talking mostly of elastic scattering of a WIMP off the nucleus of an atom, and through this process we have been searching for many physics models, WIMP interaction, such as the spin-independent dark matter scattering, because there the coherence of the scattering over all the nucleons is relevant. Or we have been looking for the scattering of a WIMP, the coupling of a WIMP through the spin of the nucleon. And in xenon, for instance, we have many isotopes which have spin, and so on and so forth, and many other, also pion coupling, WIMPs through the pion coupling process. However, I want to point out that more recent here, detectors such as ours, which give us both nuclear recoils and electronic recoils, as we call them, are able also to search for WIMP interaction, non-standard WIMP interaction, such as dark photons from the dark sector or axion-like particles, super WIMPs. We look for the energy which is imparted not to the nucleus of the atom, but to a shell, an electron of the atoms, or a combination of the two. For instance, we have been looking for inelastic magnetic dark matter in Xenon 100. Okay, so that's just a precision, something to point out. The first challenge was the small energy. The second challenge of direct detection experiment is the extremely low interaction rates. How many events we expect to see in a detector if we build one to search for it. And here you see it because the differential rate, the amount of event that we expect, is proportional to how many nuclei, how many atoms I have, how many targets I have, and it's proportional to the density of these WIMPs in the halo of this Milky Way, and also to the velocity distribution. How do they move in this galaxy? And it's also proportional to the cross-section, the interaction cross-section, which we usually take from some theoretical model, d sigma dr, and of course it's inversely proportional to the mass of the particle. So that's the basic equation of which gives us the rate, simplified. So if we plot or calculate the rate, and this is shown in events per kV, unit energy, unit mass, in this case ton, 1,000 kilogram of stuff per unit time in 1 year. Here is shown the rate as a function of recoil energy, the observable that I can measure, for 3 elements, 3 targets. The xenon, germanium, and argon. These are 3 leading target candidates for dark matter direct detection. And the calculation, you have to assume a cross-section and a mass. Here is done for every WIMPs, let's say 50 GeV particle, for a cross-section of 10 to the minus 46 square centimeter. That's a very tiny cross-section, but that's close to the level that we have been excluded so far with our direct detection experiment. And what you see, the message here is that this rate falls off exponentially. And in xenon, the red curve, you have many more events compared to the other targets, because xenon has a big atomic number, 131. It has a lot of nucleons. The scattering is coherent over all these nucleons. And so if the threshold, if the limit of energy which I can sense with my detector is low enough, in this case 10 keV nuclear recoil, I could, and if the WIMP interacts at that cross-section with a 50 GeV of mass, I would expect in my detector 15 events in my 1 ton of detector if I wait for 1 year. So it's a 15 events per year in 1 ton, which is already quite daunting compared to the overwhelming rates which comes from backgrounds of different types that I'll tell you in a moment. The other thing that you want to notice from this slide, on the right-hand side is the same calculation, but now it's for a low mass. We have been searching recently much more in the low mass region, sub-GeV or GeV particles. Here is for a low mass 4 GeV WIMP, and what you see for a cross-section 10 minus 40, that the rate falls even more steeply for xenon, definitely for a low mass particle. A lighter element such as neon, shown there in pink or whatever is the name, and silicon, for instance, are more appropriate to scatter such a light particle off. So the second challenge is this extremely low rate, few events, maybe 15 events per ton per year. And the last, for me, I think, the holy grail or the most important challenge of this experiment has been and remains to actually find this signal in a sea of background. We are not just waiting for the WIMP to give us those few events. We have events from radiation of all kind. And so the first thing is that if I place a detector in this room, I will be bombarded, the rate will be overwhelmed by the rate induced by cosmic ray muons. And so that's the first reason why these experiments are placed deep underground in a proper laboratory under kilometers of rock, or in a mine, in a deep mine, so under the surface of the Earth, to shield ourselves from the muons, cosmic radiation, which is attenuated by depth. And so even if we go deep underground, we have the last enemy, one of the enemy of this detection is neutrons, which are induced from these muons, because even as we go deep, they're not completely killed, these muons. So we have neutrons from muons, we have neutrons from materials, radioactivity. Still, these experiments is radioactive. We are very radioactive, and especially now I'm very radioactive. When I talk, I'm more radioactive than ever. so we have radioactivity from materials, and in terms of neutrons from spallation or from alpha-N reaction, that's another enemy that we have to fight, and I'll tell you a little bit how we do that. We have also from from radioactivity, we have also other type of radiation, potassium-40, cobalt-60 in the steel, all kind of radioactivity, gamma and beta emitters, which come with our materials. And ultimately, we have neutrinos. Neutrinos from the sun, neutrino, atmospheric neutrino. We have hopefully supernova neutrinos sooner or later. coming into the xenon detectors. And so these neutrinos constitute our ultimate background because we cannot do anything about it. So we cannot shield ourselves from this neutrino. In fact, they will become our signal, and that's my dream. We often call it the ultimate background of these experiments as we move forward. But for me, it gives me the hope to see a signal, because it would be phenomenal at least to see a signal from solar neutrino through coherent, for instance, scattering in xenon. So this is the key challenge, and that's been really an effort of the xenon and every other experiment to reduce the amount of both radioactivity, to search for low radioactive materials. You can imagine if I'm building a vessel which contains my xenon, I need to search for the steel, which is, if I use stainless steel, I have to beg company producer of stainless steel to let me measure and try plates after plates after plate until I identify the lowest activity cobalt 60 stainless steel, which I can use to build my vessel, and so on and so forth. Every nut and screw that we use in the xenon experiment has been screened, as we say. We measure it with high sensitivity germanium detector, with neutron detectors, to estimate their level of background and therefore predict how much rate we can get from that radioactivity. It's been painful, but we have succeeded, as I will show you, to achieve the lowest background in any dark matter detector to date. So for me, that's the greatest challenge. The sum of all these things that I told you so far, and I'm taking too much time already, is that detectors have to be massive. The more N, the more atom, the more target nuclei or atoms you have, the better. So massive detector with very low energy threshold to seize the rate, which is highest at low energy. And you have to have very low, very quiet detector, very low background, as we say, detector. And so people have been inventive in using a variety of techniques and a variety of materials to search for this dark matter directly in the laboratory. What we're looking for, again, is how to detect the energy which is deposited in a target by a dark matter particle. And when you have radiation in most material, what happens is that you can excite the atoms of these materials, and through the excitation you have scintillation, light. You produce ionization electrons, so you have charge, and you also shake the crystal. If it is a crystal form, you produce, if you like, heat or phonon, and that's another channel. And the majority of the experiments which are listed here are using two of these signals, either charge or light, or just charge and phonons, to make the best out of the detector, because, as we said, the key is to have as many handles to understand signal from background. So there is a large number of experiments which is either running, have been operated in the past, but the key is that the liquid xenon-based detectors have maintained leadership and have been at the frontier of this field. And this is a plot both for a 5 GeV WIMP cross-section and a 50 GeV WIMP cross-section, a plot of the sensitivity, if you like, or the cross-section as a function of time. And as David, I guess, alluded to, we have been able to see orders of magnitude in this cross-section, excluding WIMP interaction, spin-independent type, over the years, over the last 10, 15 years, by orders of magnitude. And so the reason why
interested in doing is exploiting the information that's left behind, either by designing a material or its manipulation, and I want to see how that would work. So there's a quote that I like very much from the choreographer Twyla Tharp. She says, there are as many forms of memory as there are ways of perceiving, and every one of them is worth mining for inspiration. And so I think that's really nice, and it kind of says what we should be all after is to mine things for inspiration. And I just want to point out a couple of memories to start off with here so that we kind of see what's going on. And so the first one is simple and obvious. And so here is the simplest memory I can think of. It's a ruler, right? And so what this does is, you put a mark at one end, you put a mark at the other end, and with this one ruler you're able to measure things, and it's a memory built into the ruler. So that's the obvious and simple kind of memory. There's other memories which are more subtle and take a little bit of surprise, and so I want to show one of those here. And so this is a memory that it's a well-known demonstration over many years, but we built this just so it could get through the airport security. So it's got less than 3 ounces of fluid in here, so we're able to get it through. And what it is in the center of this there is a big cylinder of nylon, and outside there's this plastic that you can see through, and in between that we filled it with liquid. Okay, and you can't see the liquid. I can twirl this around, right, and you don't see much happening to the to anything in there because it's just transparent liquid, and you just see the white thing, nylon circulating. So what I want to do is I want to show you what's happening inside the fluid, and so I'm going to put a little bit of dye in here and see if we can't get this dye in here. So. Okay, so that's supposed to be an S for Simons. What else? And so we can see this, and so let's see. So you can all see that that's everywhere here. So you can all see that it's on the screen as well. So for you. And now what I'm going to do is I'm going to take this this fluid and I'm going to mix it up, right? And so I'm just going to turn this around, and clearly I've mixed this thing up, and I turned it around quite a bit, and now I'm going to undo that, and it's mixed up. And so when you mix something up, it stays mixed. I mean, that's one of the great laws of physics. I mean, I think it's a physics law. Well, let's see how good physics works. And so I'm going to now turn this in the opposite direction. Whoops, I hope it works. Yeah. Okay. So you don't know how I suffered to get this to you. But anyway, so I'm glad it works. I've performed this, hundreds of times now in front of people, and every time it comes back to them, there's a pit in my stomach that says, it's not going to work this time. But, it always does. And so what is the point of this as well for the thing tonight is that I want to show you that, okay, even though it wasn't clear that it was there was a memory that this material had of how I have manipulated it in the past. And the question is, well, can I manipulate things in a way that then becomes useful in some serious way? Yeah.
Is it only depends on the type of liquid, or will not work with everything?
Well, so this is I didn't want to get into this so much because that's not particularly the topic. But this is the liquid in here is called glycerol. You may know of it because it's if you put into you can buy it in a drugstore and you can put it to make big bubbles, soap bubbles, and make them bigger. But you also may know it because I've been told at least that McDonald's puts it in their shakes to give it that je ne sais quoi de McDonald's, and so that's what we have here. Okay, so it doesn't work with water with this apparatus, but if I made it really, really, really thin, so there's a dimensionless number that I have to get small, and water is, so it had to have gaps 1,000 times smaller, etc. In order to see it. But that's but any fluid that I'm in that limit with should work this way. Okay, and so and glycerol just makes it visible for us. Okay, so that is two memories that I want you to see. And so now what I want to talk about this evening is all based on ideas that have come from our collaboration. And so at the top row I have some of our PIs, Andrea Liu and Mathieu Piard, and some of our affiliates, Carolina Brito and Shrikant Sastry. And so these are the people whose ideas have spurred this kind of work that I'm going to be telling you about tonight. And then there were a bunch of students and postdocs here, and they're the ones who actually did all the work. And the ones that I have in outlined are the ones whose work I'm really going to be talking about tonight. So Daniel Hexner is a postdoc with us. Jason Rox is a graduate student at University of Pennsylvania. Nidhi Pashini is a graduate student in my group at Chicago. Okay, so these are the people whose work I'm going to be talking about. And now about the talk, there are going to be three parts to the talk. The first part is the missing half, and it's about our disordered world and about the new laws that you get when you think about disorder. And the main purpose of this part is to say that the disordered matter is different from crystalline solids, and so I want to show you that and show how that works. The second half of the talk is about malleability of disorder, and that because of the disorder you get new design rules that allow you to make new kinds of things, and so that's the second half. The third half of the talk is about directed aging, and so this is an idea where we want to get the materials to train themselves to have these properties, and so those are the three aspects that I'm going to be going through. Okay, so the first part is the missing half, our disordered world, and the new laws that come about. So what I want to emphasize at the beginning is that glasses are different from crystalline materials, from ordered materials, and you can see this by their structure. And so here in red at the top is a disordered material, a glass, a jam system, and you can see the particles are not in any particular obvious order. On the right, I have a crystalline material where every atom is in a crystalline lattice, and it has all the symmetries of the lattice. Below that, I have something that's perhaps more interesting, is somehow the phase space in which these materials live. That is, for a glass or a jam system, the landscape, potential energy, free energy landscape, is very rough, and so there are many minima in such a landscape. Whereas for the crystal, you only have one very deep minimum. And so this creates a lot of opportunity. On the one hand, these glasses are going to be more adaptable. That is, because there are so many different minima, you can try to train it to be in one minimum versus another. And in the aspect of training, you can have multiple paths to go from one minimum to another. And so these are some of the ways in which glasses could be useful. And so this flexibility, we want to harness this for novel behavior. So how does disordered matter compare to a crystal? And so I show here just a schematic of a disordered system, and it obviously is not a crystal. That is, it's not in a lattice. It has the structure that's more like what you would get from a liquid. But if it's just aspect of this system. I mean, I was told when I was a kid to look out the window, that window pane in front of me was somehow supposed to be different from everything else around me, and I couldn't get it. I mean, I just didn't see it. It was hard. I rapped on it, and it rapped back. I mean, it didn't seem in any way different. And if all you had to do was go to an X-ray machine to see that the particles were not actually in an ordered array, well, so they're not an ordered array. I mean, that doesn't tell you that much. The question is there other things about this being a disordered array that makes this an exciting problem? And what I want to show you is there is much, much more, and that's why we're excited about this. And I'm only going to tell you about two aspects of this tonight, because that's all I have time for. But one has to do with the elasticity of such a medium, of a material that's glassy versus crystal, and the other is this idea of aging. And materials age over time, and you don't get that with a crystal, which is already in its equilibrium position, but glasses can age because they are searching for a better and better ground state, and they can do this over time. And so that's one of the things that makes this unique. So how do we make a disordered material that really has rigidity of the same kind that you might want to compare? And so I talk about jamming as just one example of how we could get a material of this kind. And the idea is really very simple. The idea was you just take a big box, and in this big box you throw in a bunch of particles, and if the particles aren't too many, they can push each other apart, and they no longer interact with one another, and this thing can flow easily from one side to the other. There's nothing special about where the particles are, because they can flow. if you compress this thing too much, this thing clearly becomes overjammed, and so this thing the particles overlap with one another, and they can no longer move. You can't compress them without paying energy to compress them, and you can't shear them. So you have to put energy in to do anything, any macroscopic deformations of this system. There's a point in the middle, which is just where these particles are forced to interact with one another. I mean, there's where they just touch, and if you push them any more, then they would start to push back. And so this is the jamming transition. And so this is where what happens at t equals 0. And this is a wonderful material at that jamming transition. It has all sorts of wonderful properties, which I won't talk too much about this evening. But it's this is the kind of type of system that could show very disordered material behavior on one side, and then you can tune it back towards where it just becomes rigid at this jamming transition. Okay, so I said I was going to say a little bit about elasticity, and I don't want to say too much, but just the idea of, well, how do we talk about elasticity of a material? Well, you want to know how it responds. And so the one thing I'm going to talk about is this idea of compressing this material. So I compress it on all sides uniformly. And that costs energy to do that because I'm pushing these particles into one another. And so that's that energy is a measure of what's called the bulk modulus of the material. So that's one of the moduli. Another modulus you could do would be, suppose I took this material and I tried to shear it. That would also cost energy, and the energy of shearing would then be tell you what this shear modulus is going to be like. So the bulk modulus B and the shear modulus G is what's two of the major characteristics of any material. And in crystals, what you always find is that the shear modulus G is comparable to the bulk modulus B. And you can kind of see that easily, because if you took two particles and you tried to jam them together, well, they're pushing up against each other, and they're trying to push back, and that's the energy you're paying. That is how much you're pushing one particle into another. And so that's the bulk modulus. But if you were trying to shear it, you would be trying to push one past another, but that's just changing the angle a bit so that you're still pushing one particle into another, and so you're still working against that same interparticle potential. And so the shear modulus is going to be kind of the same as the bulk modulus. It should have the same scale. Maybe it's off by cosine theta, but who cares about a cosine theta? That's the idea of this. And so all crystals are going to have this idea that the shear and bulk modulus are of the same order of magnitude, a factor of a third or something, but nothing tremendous. But if you look at a jam system, this ratio, G over B, goes to 0 at this transition. And so that's really quite special. That's saying that the shear modulus is infinitely weaker to shear a system than to compress it. And so that's something new. That's something that we didn't have in a crystal. And so this already kind of hints that there's a greater flexibility due to disorder. That is, if you didn't have this flexibility, you would have been stuck at one value of G over B. But here, we can tune it all the way from being comparable to being one infinitely weaker than the other. Okay, so to make things simple for us tonight, and so this is a simplification, is we're going to take these jam systems, and I'm just going to make a network out of them. So I start with the jam system. I know where all the particle spheres are, and at every sphere, I've located center. I replace that with a node, and every place where there's an overlap between two particles, I replace that with a spring. And so I start off with the black circles, which are the original jam packing, and I replace that then with just this network, which has exactly the same geometry and topology as the jam system, and it just has a simplification that I only have the bonds between these nodes to worry about, and the elasticity should be quite similar. And so this is a simplification that I'm going to work with this evening. Okay, so what do we want to do? I showed you earlier this rugged energy landscape, and one of the things that we want to do is we want to understand, well, what is the nature of the minima in this landscape? And so we want to explore this landscape, and you can do this in a number of ways. One way is to raise the temperature, and so you can move from one point to another on this landscape, or you could shear this thing, as I was just telling you about before. But there's a third way, which is something that we've been studying in this collaboration, which is you can actually go in and microscopically manipulate this system and really examine in much more detail what's happening in each of these minima wherever you happen to land. And you do this by going into this network, and you can snip a bond. And it's okay, so snipping one bond, what does that do to my network, the elastic properties or the physical properties of the system after I've done that? So that's the thing that we're going to be trying to understand tonight. So the idea here is I want to look at what I call bond level response. So bond level response is I have my whole system, and I measure its bulk modulus, and I measure its shear modulus. I know what that is for the original system. And then I go in at random, and I pick one bond, and I pluck it out. And I measure, okay, what's the new bulk modulus? What's the new shear modulus? And I make a note of that. And then I put that bond back, and then I go in and pick another bond at random, and I do the same thing over and over again. So I can find out how each bond in the system changes the elastic properties. Well, this would really be quite dull if I had started with a crystal. In the crystal, every time I take a bond out, it changes the moduli. I put it back and I take another bond out. Well, since every bond is the same in the crystal, it does the same thing, it doesn't matter. That is, it doesn't matter which one I take. So every bond removal will give me exactly the same value of the change in the modulus. It's a delta function. Nothing is happening except that I get everything being the same. Okay, so this is rather dull. And so you can ask, well, suppose we started with our jam system and we did that. What would we get? And so here I have a picture of what, at least when we started this, what I thought this thing would look like, which would be, okay, it broadens that delta function out, and that some would be a little bit more important for the bulk modulus, some a little bit less, but on average they would all be about what that bulk modulus is. Well, that's not what nature does. Nature does the following, and so you can see dirty works afoot because this is now a log scale, so that it's really very, it's showing that I have a vast variation in what this behavior is. this is a probability of getting a change in bulk modulus of a certain amount, delta B, or the shear modulus, delta G. I plot them both on here because one thing is surprising is that it's the same curve. It doesn't matter which one it is. Both of these things have the same distribution. The second thing about this, which is very important, is that, remember before I just had basically a delta function with a Gaussian around it. Here, this doesn't look like that at all. What it is a curve that is incredibly broad. It goes all the way down to 0. It has a nice feature that it has this basically power law behavior. We can understand all of these properties, but I'm not interested in explaining those tonight. I just want to say, oh, look, this is really quite different. This is very different from what I would have guessed I would get in a crystalline system. And so, can we use this in some way? Or what can this be good for? And so their distributions are broad, continuous, and universal. And one other thing that was really the major surprise here is I would have thought that if I had a material that had a distribution of contributions of a bond to something, if I take out a bond and it was really, really important for, let's say, the bulk modulus, that bond would also be important for the shear modulus. I mean, if a bond is important, it's important, right? It plays an important role. What this curve is also showing, because there are many data points hidden in that line, is it doesn't matter which, these two things are totally uncorrelated. That is, if you took a bond here that was very, very important for the bulk modulus, and asked what did that bond do for the shear modulus, it's equally likely to have come from any place in this whole curve. So